Introduction.
Father, what is the full form of LPG?
What are you doing?
I'm studying hydrocarbons. Our teacher has asked us to read about hydrocarbons.
Oh, that's good. Do you need any help?
Yes, I'm reading but not able to understand.
We use kerosene oil for domestic use. Petrol, diesel and CNG are used in automobiles. All these fuels contain hydrocarbons. Isn't it interesting?
Very interesting. Please tell me more about hydrocarbons.
Sure. Come, let's start. Objectives. At the end of this lesson, you will be able to define hydrocarbons, understand the classification of hydrocarbons, explain alkanes, name hydrocarbons according to IUPAC system of nomenclature, recognize and write structure of isomers of alkanes, learn methods to prepare alkanes, write the physical and chemical properties of alkanes, explain the conformations of ethane. Definition. Hydrocarbons, composed entirely of carbon and hydrogen, are the most important family of organic compounds. The organic compounds of simplest composition and may be considered the parent substances from which all other organic compounds are derived. The hydrocarbons are conveniently classified into two major groups, open chain and cyclic. Open chain compounds containing more than one carbon atom. The carbon atoms are attached to each other to form an open chain. The chain may carry one or more side branches. In cyclic compounds, the carbon atoms form one or more closed rings. The two major groups are subdivided according to their chemical behavior into saturated and unsaturated compounds. Classification. Depending upon the types of carbon-carbon bonds present, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated. Saturated means that each carbon is bonded to four other atoms through single covalent bonds. Hydrogen atoms usually occupy all available bonding positions after the carbons having bonded to each other. Unsaturated. Unsaturated hydrocarbons contain either double or triple bond. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double or triple bonds. Aromatic hydrocarbons. Aromatic hydrocarbons are a special type of cyclic compounds. We can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. Alkanes. Hydrocarbons which contain only single bonds are called alkanes. They are called saturated hydrocarbons because there is a hydrogen in every possible location. This gives them a general formula CnH2n plus 2. The first four alkanes are methane, ethane, propane and butane with the Lewis symbol as shown. Alkyl groups. An alkyl is basically an alkane minus one of its hydrogen atom. For example, if methane removes one hydrogen, we will get methyl. Similarly, if ethane removes one hydrogen, we will get ethyl. IUPAC system of naming alkanes 1. The IUPAC, International Union of Pure and Applied Chemistry, is composed of chemists representing the national chemical societies of several countries. One committee of the IUPAC, the Commission on Nomenclature of Organic Chemistry, has set a system of naming organic compounds. The last syllable in the name of compound designates the family to which it belongs. The alkanes all end in -ane. IUPAC rules for naming the alkanes. Number 1. The name ending for all alkanes and cycloalkanes is -ane. Number 2. The parent chain is longest continuous chain of carbons in the structure. For example, the branched chain alkane is regarded as being made from the following parent: CH3, CH2, 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 CH3 by replacing an H on the third C from left with CH3. Number 3. The carbon atoms of the parent chain are numbered starting from whichever end of the chain gives the location of the first branch, the lower of two possible numbers. For the example, given the correct direction is from left to right. RUPSA system of naming alkanes part 2. Number 4. Name each branch attached to the parent chain according to alkyl groups. In this case, the branch would be methyl. Number 5. Attach the name of the alkyl group to the name of the parent as a prefix. Place the location number of the alkyl group in front of the resulting name. In this case, it would be 3-methylhexane. Number 6. When two or more groups are attached to the parent, name each and locate each with a number. The alkyl substituent names are assembled in alphabetical order. Always use hyphens when separating numbers from words. The following is po-ethyl to methyl heptane. Number 7. When two or more substituents are identical, use prefixes such as di for 2, tri for 3, tetra for 4 and specify the location of every group. Always separate a number from another number in a name by a comma. The following is 2,4 dimethylhexane. Number 8. When identical groups are on the same carbon, repeat the number of the carbon in the name. The following is 2,2 dimethylheptane. Number 9. Sometimes you may need to go around corners and zigzag to find the longest parent chain. The following is 3,4 dimethylheptane. Preparation of alkanes part 1. Decarboxylation. Decarboxylation means removal of CO2 from molecules having COOH group. Saturated monocarboxylic acid, salt of sodium potassium on dry distillation with soda lime gives alkane. Wood's reaction. A solution of alkyl halide in ether on heating with sodium gives alkane. By reduction of alkyl halides. Alkyl halides on reduction with nascent hydrogen form alkanes. Preparation of alkane part 2. By hydrogenation of alkanes. Sabatier and Sanderin's method. Alkenes and alkynes on catalytic hydrogenation gives alkanes. Kolbe's electrolysis method. Alkanes are formed on electrolysis of concentrated aqueous solution of sodium or potassium salt of saturated monocarboxylic acids. Electrolysis of an acid salt gives symmetrical alkane. However, in case of mixture of carboxylic acid salts, all probable alkanes are formed. Physical properties of alkane. State. Number 1. All are colorless and possess no characteristic odor. Number 2. Lower alkanes C1 to C4 are gases. Middle one C3 to C17 are liquids and higher are solids. Number 3. The boiling point of alkanes increases with increase in molecular weight due to increase in van der Waals forces with increase in molecular weight, that is, boiling point order. Pentane is less than hexane is less than heptanes. Number 4. Also the branching in alkanes gives a decrease in surface area as the shape approaches to spherical, which results in decrease in van der Waals forces. That is why boiling point of isomeric alkanes whose order is pentane is greater than isopentane is greater than neopentane. Number 5. The melting points of alkanes do not show a regular trend. Alkanes with even number of carbon atoms have higher melting point than their adjacent of odd number of carbon atoms. Melting point order is propane is less than ethane is less than methane. Number 6. The abnormal trend in melting point is probably due to the fact that alkanes with odd carbon atoms have their end carbon atom on the same side of the molecule and in even carbon atom alkane, the end carbon atom on opposite side. Thus, alkanes with even carbon atoms are packed closely in crystal lattice to permit greater intermolecular attractions. B. Density. The density of alkanes increases with increase in molecular weight and becomes constant at 0.76 gram per milliliter. Thus, all alkanes are lighter than water. C. Solubility. Number 1. Alkanes being non-polar and thus insoluble in water but soluble in non-polar solvents. Example, C6H6, CCl4, ether, etc. Number 2. The solubility of alkanes decreases with increase in molecular weight. Number 3. Liquids, alkanes are themselves good, non-polar solvent. Chemical properties of alkanes Part 1. Alkanes are quite inert substances with highly stable nature. Their inactiveness has been explained as: Number 1. In alkanes, all the carbon-carbon and carbon-hydrogen bonds being stronger sigma bonds and not influenced by acids, alkalis, oxidants under ordinary conditions. Number 2. The carbon-carbon completely non-polar and carbon-hydrogen weak polar bonds in alkanes are particularly non-polar because of small electronegativity difference in C 2.6 and H 2.1. Thus, polar species, that is, electrophiles and nucleophiles, are unable to attack these bonds under ordinary conditions. In spite of less reactive nature, alkanes show some characteristic reactions. Oxidation. Oxidation of alkanes gives different products under different conditions. Alkanes are heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. Higher alkanes on oxidation in presence of manganese acetate give fatty acids. Incomplete oxidation of alkanes in limited supply of air gives carbon black and carbon monoxide. 2CH4 plus 3O2 gives us 2CO plus 4H2O. CH4 plus O2 gives us C plus 2H2O. Chemical properties of alkanes 2. Substitution reactions. Number 1. Substitution in alkanes shows free radical mechanism. For mechanism, see free radical substitution. Number 2. Following substitution reactions in alkanes are noticed. Halogenation. Number 1. Replacement of hydrogen atom of alkane by halogen atom is known as halogenations. Number 2. Halogenation of alkane is made on exposure to halogen plus alkane mixture to ultraviolet light or at elevated temperature. Number 3. The extent of halogenations depends upon the amount of halogen used. Isomerization. Number 1. The process of conversion of one isomer into other is known as isomerization. Number 2. Straight chain alkanes are heating with AlCl3 plus HCl at about 200 degrees centigrade and 35 atmospheric pressure are converted into branched chain alkanes. Chemical properties of alkanes Part 3. Aromatization. Number 1. The process of conversion of aliphatic compound into aromatic compound is known as aromatization. Number 2. Alkanes having 6 to 10 carbon atoms are converted into benzene and its homologous at high pressure and temperature in presence of catalyst. Dehydrogenation. Alkanes are dehydrogenated on heating in presence of catalyst to produce corresponding alkenes. Pyrolysis. Number 1. The decomposition of a compound on heating in absence of air is known as pyrolysis. Number 2. The phenomenon of pyrolysis of alkane is also known as cracking. Number 3. Alkane vapors on passing through red-hot metal tube in absence of air decompose to simpler hydrocarbons. The product formed during cracking depends upon A. Nature of alkane, B. Temperature and pressure, C. Presence or absence of catalyst. Here is the example of cracking. Conformations. The different spatial arrangements that a molecule can adopt due to rotation about sigma bonds are called conformations, and hence conformational isomers or conformers. The study of the energy changes that occur during these rotations is called conformational analysis. This is important because the structure of a molecule can have a significant influence on the molecular properties, including dictating the outcome of a reaction, although the ideas are developed for the simplest functional groups, the alkanes. The same principle can be expanded and applied to other functional groups. For alkanes, various conformations can be represented by using dash wedge notation in a structural perspective drawing. An alternate depiction is a Newman projection, which views a molecule by looking down at C-C bond axis, showing the relative orientation of groups of the two carbon atoms. Conformational analysis of ethane. Conformational analyses are assisted greatly by a representation of molecules in a manner different to skeletal structure. A representation of a molecule in which the atom and bonds are viewed along the axis about which rotation occurs is called a Newman projection. In a Newman projection, the molecule is viewed along an axis containing two atoms bonded to each other and the bond between them, about which the molecule can rotate in a Newman projection. The substituents of each atom composing the bond, be they hydrogen or functional groups, can then be viewed both in front of and behind the carbon-carbon bond. Specifically, one can observe the angle between a substituent on the front atom and a substituent on the back atom in the Newman projection, which is called the dihedral angle or torsion angle. In ethane specifically, we can imagine two possible extreme conformations. In one case, the dihedral angle is 0 degree and the hydrogens on the first carbon line with or eclipse the hydrogens on the second carbon. When the dihedral angle is 0 degree and the hydrogens line up perfectly, ethane has adopted the eclipsed conformation. The other extreme occurs when the hydrogens on the first carbon are as far away as possible from those on the second carbon. This occurs at a dihedral angle of 60 degree and is called the staggered conformation. The staggered conformation of ethane is more stable than the eclipsed form by 12.1 kJ per mole, so that as one methyl group rotates 360 degree relative to the other, the compound passes through three stable staggered conformers via three unstable eclipsed forms. This barrier is small enough that at 25 degrees Celsius, the compound changes conformation about 50 million times each second. Sawhorse projection. Sawhorse projections are very similar to Newman projections, but are used more often because the carbon-carbon bond that is compressed in a Newman projection is fully drawn out in a sawhorse projection. When properly laid out, sawhorse projections are useful for determining enantiomeric and diastereomeric relationships between two molecules because the mirror image or superimposability relationships are clearer. Like with the Newman projections, a sawhorse projection is a view of a molecule down a particular carbon-carbon bond, and groups connected to both the front and back carbons are drawing using sticks at 120-degree angles. Sawhorse projection can also be drawn so that the groups on the front carbon are staggered, 60 degrees apart, or eclipsed, directly overlapping with the groups on the back carbon. Below are two sawhorse projections of ethane. The structure on the left is staggered and the structure on the right is eclipsed. These are the simplest sawhorse projections because they have only two carbons and all of the groups on the front and back carbons are identical. Did you know? In petroleum geology and chemistry, cracking is the process whereby complex organic molecules such as heavy hydrocarbons are broken down into simpler molecules, such as light hydrocarbons, by the breaking of carbon-carbon bonds in the precursors. The rate of cracking and the end products are strongly dependent on the temperature and presence of catalysts. Cracking is the breakdown of a large alkane into smaller, more useful alkanes and alkenes. Simply put, hydrocarbon cracking in this process of breaking long-chain hydrocarbons into short ones. Summary. Let us summarize what we have learned. Hydrocarbons are the compound of carbon and hydrogen only. Hydrocarbons are mainly obtained from coal and petroleum, which are the major source of energy. Hydrocarbons are classified as open-chain saturated and unsaturated cyclic and aromatic according to their structure. The important reactions of alkanes are free radical substitution, combustion, oxidation, and aromatization. Alkanes show conformational isomerism due to free rotation along the C-C sigma bonds out of staggered and eclipsed conformations of ethane. Staggered conformation is more stable as hydrogen atoms are farthest apart. Introduction.
Don't scrub, Ankush. Let me study.
What are you studying?
I'm doing my homework of chemistry.
You are doing wrong.
What are you doing?
Now this is correct.
No, this is double bond and this is an alkene.
Teacher has taught us about single bond and alkanes, but she did not teach alkenes. What are they?
Alkenes are unsaturated hydrocarbons and so are alkynes. Come, I'll tell you in detail about alkenes and alkynes.
Objectives. At the end of this lesson, you will be able to explain alkenes and alkynes, name alkenes and alkynes according to IUPAC system of nomenclature, recognize and write structures of isomers of alkenes and alkynes, learn methods to prepare alkenes and alkynes, write the physical and chemical properties of alkenes and alkynes. Alkenes. Alkenes are class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Since the compound is unsaturated with respect to hydrogen atoms, the extra electrons are shared between two carbon atoms, forming double bonds in alkenes. Alkenes are also called olefins because they form oily liquids on reaction with chlorine gas. These are the compounds of ethene or ethylene and pentene. Structure of double bond. The chemical bonding in alkenes can be illustrated by reference to the simplest alkene, ethene. Ethene is not a very complicated molecule. It contains two carbon atoms that are double bonded to each other, with each of these atoms also bonded to two hydrogen atoms. This forms a total of 3 bonds to each carbon atom, giving them an sp2 hybridization. Since the carbon atom is forming 3 sigma bonds instead of the 4 that it can, it only needs to hybridize 3 of its outer orbitals instead of 4. It does this by using the 2s electron and 2 of the 2p electrons, leaving the other unchanged. This new orbital is called an sp2 hybrid because that's exactly what it is. It is made from one s orbital and 2 p orbitals. When atoms are an sp2 hybrid, they have a trigonal planar structure. These structures are very similar to a peace sign. There is a central atom with 3 atoms around it, all on one plane. Trigonal planar molecules have an ideal bond angle of 120 degree on each side. The HCH bond angle is 117 degree, which is very close to the ideal 120 degree of a carbon with sp2 hybridization. The other two angles, HCC, are both 121.5 degrees. Nomenclature of alkenes. Step 1. Find the longest continuous chain that includes the double bond. Step 2. Use the ending end to indicate the presence of carbon-carbon. Step 3. Number of the chain so that the first carbon of the carbon-carbon reached has the lowest possible number. Step 4. Name and number substituents in the same fashion as in alkanes. This is 1-butene and these are 2-methyl-2-butene and 3-methyl-1-butene. Step 5. The alkene functional group takes precedence over alkyl and halide functional groups. Step 6. The alcohol functional group takes precedence over the alkene functional group. 4-bromo-3-methyl-1-butene. Nomenclature of alkenes, Part 2. Step 7. Hydroxyl groups takes precedence over the double bond when the chain is numbered. This compound is 2-methyl, 3-butane, 1-ol. Step 8. If more than one double bond is present, indicate their position by using the number of the first carbon of each double bond and use the suffix diene for 2 double bonds, triene for 3 double bonds, tetraene for 4 double bonds, etc. For example, 1,4-pentadiene. Step 9. Cycloalkenes are named in a similar way. Number the cycloalkene, so the double bond carbons get numbers 1 and 2, and the first substituent is the lowest possible number. If there is a substituent on one of the double bond carbon, it gets number 1. 6-ethyl 1-methyl cyclohexene. Look at this compound. It is named as 1,5-dimethyl cyclopentene and not 2,3-dimethyl cyclopentene. Isomerism. Structural isomerism. All the alkenes with 4 or more carbon atoms in them show structural isomerism. This means that there are 2 or more different structural formulae that you can draw for each molecular formula. For example, with C4H8, it isn't too difficult to come up with these 3 structural isomers. There is, however, another isomer. But-2-ene also exhibits geometric isomerism. Geometric cis-trans isomerism. The carbon-carbon double bond doesn't allow any rotation about it. That means that it is possible to have the CH3 groups on either end of the molecule locked either on one side of the molecule or opposite each other. These are called cis-but-2-ene, where the groups are on the same side, or trans-but-2-ene, where they are on the opposite sides. Cis-but-2-ene is also known as Z-but-2-ene. Trans-but-2-ene is also known as E-but-2-ene. Preparation of alkenes, Part 1. Alkenes are generally prepared through beta elimination reactions, in which 2 atoms on adjacent carbon atoms are removed, resulting in the formation of a double bond. Alkenes are usually prepared from either alcohols or haloalkanes, alkyl halides, by the dehydration of alcohols. In dehydration reactions, a molecule of water is eliminated from an alcohol molecule by heating the alcohol in the presence of a strong mineral acid. A double bond forms between the adjacent carbon atoms that lost the hydrogen ion and hydroxide group. From haloalkanes or alkyl halides. Alkenes can be obtained from haloalkanes, alkyl halides. These haloalkanes are usually bromo and iodo and less commonly chloro derivatives. Preparation of alkenes, Part 2. By dehydrogenation of haloalkanes. Haloalkanes on heating with alcoholic potash loses one molecule of hydrogen halide to give alkene. Bromoethane gives ethane. Dehalogenation. Vicinal dihalides, which are alkane molecules that contain 2 halogen atoms on adjacent carbon atoms, can form alkenes upon reaction with zinc. From alkynes. Alkenes can be easily obtained by hydrogenation of alkynes. An alkyne on controlled hydrogenation with hydrogen in the presence of Ni or Pd at 200 degrees centigrade gives corresponding alkene. Ethine gives ethene on hydrogenation. Physical properties of alkenes. Physical state. Alkenes can exist in all the 3 physical states, gases, liquids and solids at room temperature. At room temperature, lower alkenes, first 3 alkenes, are colorless gases, while next 14 members, those comprised of 5 to 15 carbon atoms, are colorless liquids. The higher alkenes are colorless solids. Except ethene, all other alkenes are colorless and odorless. Ethene has a faint sweet smell. Because of non-polar nature of alkenes, they are insoluble in water, but soluble in non-polar solvents like benzene, carbon tetrachloride and petroleum ether, etc. Density. Alkenes have densities less than 1 gram per milliliter and are therefore less dense than water, hence form separate layer above water. As the molecular mass of alkenes increases, density increases. Boiling points of alkenes. In liquid state, molecules are packed closely together with weak intermolecular force of attraction, hence can be moved randomly in system. When we supply heat to the liquid, temperature of system increases, which contributes in the increment in kinetic energy of molecules. Hence, the molecule motion increases and the forces of attraction between the molecules decreases at high temperature. Just like boiling point, melting points of alkenes also increase with an increase in the molecular mass. Chemical properties of alkenes, Part 1. Alkenes are more reactive than alkanes due to the presence of a double bond. The carbon-carbon double bond consists of a strong bond and a weak p bond. Addition reactions. The p electrons of the carbon-carbon double bond are available to an electrophile, any species seeking electrons. Thus, the addition reactions shown by alkenes are in fact electrophilic addition reactions. Addition of hydrogen. Alkenes add hydrogen in the presence of platinum or nickel catalyst to form alkanes. The reaction termed as hydrogenation is an exothermic reaction. Addition of halogens. Alkenes react with halogens to form dihaloalkanes. The order of reactivity is chlorine is greater than bromine is greater than iodine. Simply mixing together the two reactants, usually in an inert solvent like carbon tetrachloride, best carries out the reaction. Addition of halogen acids. Alkenes with concentrated aqueous solution of halogen acids give haloalkanes. The order of reactivity is Hi is greater than HBr is greater than HCl. In asymmetrical alkenes, the addition of a halogen acid takes place in a manner whereby the halogen atom, the negative part of the molecule to be added, adds to the carbon atom, which has lesser number of hydrogen atoms on it. For example, in the case of propene, the product obtained is 2-iodopropane and not 1-iodopropane. This rule of addition of halogen acids to an asymmetrical alkene is known as Markovnikov's rule. Chemical properties of alkenes, Part 2. Addition of sulfuric acid. In accordance to Markovnikov's rule, alkenes readily add concentrated sulfuric acid to form alkyl hydrogen sulfates. For example, ethene react with ethane sulfuric acid to give ethyl hydrogen sulfate. Addition of water, hydration of alkenes. Water molecules add to an alkene molecule across the double bond in the presence of dilute acid and a catalyst. For example, ethane gives ethanol when a mixture of ethene and steam is passed over phosphoric acid and silica under a pressure 65 atmosphere and at 300 degrees centigrade. Addition of ozone. Ozonides are formed when alkenes add a molecule of ozone across the double bond. For example, ethene gives ethene ozonide. Polymerization. Addition polymerization is a process by which a large number of molecules of the same species join together without the elimination of simple molecules like HX, H2O, etc. to form a giant molecule called a polymer. Alkenes undergo addition polymerization when heated under pressure in the presence of suitable catalysts. When ethene is heated to 1000 degrees centigrade under 1000 atmospheric pressure in presence of oxygen, we get polyethene. Alkynes. Alkynes are hydrocarbons which contain a triple carbon-carbon bond. As with alkenes, the simplest member of the series is 2-carbon molecule. The triple bond is indicated by changing the ending of the name to "-ine", in the same manner as the double bonds in alkenes are indicated by the ending "-ene". Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. For example, ethyne, the simplest alkyne, which is more commonly known by its common name acetylene, is a gas often used as a fuel for cutting and welding torches because it burns with a very hot flame. Naming alkynes. In IUPAC system, the alkynes are named as derivatives of alkanes. The suffix "ane" is replaced with "ine" in the alkane name. For example, the given compound has 3 carbon atoms and hence the root name is propane. If the suffix "ane" is replaced with "ine", we will get the IUPAC name of the compound as propyne. If there is a substitute in the chain, the longest chain is selected in such a way that the chain contains the triple bond. Similarly, the chain is numbered in such a way that the carbon containing the triple bond gets the least number. For example, the given compound contains 5 carbon atoms in the longest chain, hence it is named as pentyne. It is named from the right to left so that the carbon containing triple bond gets the number 1. There is one substitute methyl group at 3rd carbon atom, hence the name of the compound is 3-methyl-1-pentyne. Structures of alkynes. In the structure of alkynes, the carbon atom undergoes sp hybridization. The outermost electronic configuration of carbon is 2s2 2p2. In the excited state, one electron from 2s orbital is excited to 2p. Hence, the electronic configuration in the excited state is 2s1, 2px1, 2py1, 2pz1. Here, the carbon undergoes sp hybridization to give 2 sp hybridized orbitals with linear shape and with bond angle as 180 degrees. One of the sp hybridized orbitals is connected with other carbon and other is connected with hydrogen. Hence, the structure of acetylene molecule is linear. Isomerism. Chain isomers. Compounds having same molecular formula with different in carbon chain pattern like linear or branch are called chain isomers. 1-pentyne is chain isomer of 3-methylbutane. Position isomers. Compounds having same molecular formula with difference in position of the functional group are called as position isomers. 1-butane and 2-butane are position isomers. Functional group isomers. Compounds having same molecular formula with difference in nature of functional group are called as functional group isomers. Alkynes are functional group isomers for cycloalkenes. For example, pentyne and cyclopentene are functional group isomers. Geometrical isomers. The bond between carbon atoms in alkyne is rigid and cannot be rotated. Hence, there should be possibility of geometrical isomers. But the orientation of atoms cannot be determined. Hence, there is no possibility of geometrical isomerism in alkynes. Preparation of alkynes. The preparations of alkynes are very similar to those of the alkenes. The main preparative reactions involve the elimination of groups or ions from molecules, resulting in the formation of pi bonds. Dehydrohalogenation. The loss of an hydrogen atom and a halogen atom from adjacent alkane carbon atom leads to the formation of an alkene. The loss of the additional hydrogen and halogen atoms from the double bonded carbon atoms leads to the alkyne formation. The halogen atoms may be located on the same carbon, a geminal dihalide, or on adjacent carbons, a vicinal dihalide. During the second dehydrohalogenation step, certain conditions are necessary, namely high temperatures and an extremely strong basic solution. Dehalogenation. Vicinal tetrahaloalkanes can be dehalogenated with zinc metal in an organometallic reaction to form alkynes. Substitution. Larger alkynes can be generated by reacting an alkyl halide with an acetylide ion, which is generated from a shorter alkyne. Ethyne acetylene preparation. Ethyne, which is commonly called acetylene, is the simplest alkyne. Historically, it was prepared by reacting calcium carbide with water. Today, ethyne is normally prepared by the pyrolysis of methane. In this procedure, a stream of methane gas is briefly heated to 1500 degrees centigrade in an airless chamber. Air must be excluded from the reaction or oxidation combustion will occur. Physical properties of alkynes. The physical properties of alkynes are very similar to those of the alkenes. Alkynes are generally nonpolar molecules with little solubility in polar solvents, such as water. Solubility in nonpolar solvents, such as ether and acetone, is extensive. Like the alkanes and alkenes, alkynes of 4 or fewer carbon atoms tend to be gases. Substituted alkynes have small dipole moments due to differences in electronegativity between the triple bonded carbon atoms, which are sp hybridized, and the single bonded carbon atoms, which are sp3 hybridized. The sp hybridized carbon atom, which possesses more s character than the sp3 hybridized carbon atom, is more electronegative in character. The resulting asymmetrical electron distribution in the bond between such carbon atoms results in the generation of a dipole moment. Chemical properties of alkynes. Combustion. Alkynes burns in air or oxygen with smoky flame. Addition of hydrogen. An alkyne reacts with hydrogen in the presence of catalyst, Pt or Ni, at 250 degrees centigrade, first forming alkenes and finally alkanes. Addition of halogens. Alkynes react with halogens, Cl2 or Br2, in the dark, forming dihaloalkenes, first and finally tetrahaloalkanes. The reaction gets accelerated in the presence of light or halogen carriers. Addition of water. In the presence of sulfuric acid, 42% and 1% mercuric sulfate at 60 degrees centigrade, alkynes add on one water molecule to give aldehydes or ketones. For example, ethine gives ethanol and propine gives acetone. Polymerization. On heating, alkynes undergo polymerization in the presence of catalyst. The nature of products depends upon the conditions. For example, when ethyne acetylene is passed through a hot copper tube, it polymerizes to benzene. When passed through a solution of cuprous chloride in ammonium chloride, ethyne undergoes linear polymerization. Did you know? Markovnikov's rule was formulated by the Russian chemist Vladimir Vasilievich Markovnikov in 1870. Mechanisms that avoid the carbocation intermediate may react through other mechanisms that are regioselective against what Markovnikov's rule predicts, such as free radical addition. Such reactions are said to be anti-Markovnikov, since the halogen adds to the less substituted carbon, exactly the opposite of Markovnikov reaction. Again, like the positive charge, the radical is most stable when in the more substituted position. Summary. Let us summarize what we have learnt. Alkenes are a class of hydrocarbons which contain only carbon and hydrogen. Two other terms which describe alkenes are unsaturated and olefins. Unsaturated hydrocarbons contain either double or triple bonds. Alkynes, like alkenes, are unsaturated hydrocarbons with the general formula CnH2n-2. They are very unstable and quite reactive. Alkenes and alkynes undergo addition reactions, which are mainly electrophilic additions. Alkenes exhibit geometrical cis-trans isomerism due to restricted rotation around the carbon-carbon double bond.
Introduction. Students, look at this structure. Does anyone know what is this? Sir, this is a benzene ring. Correct, a benzene ring. And now, who will define aromatic hydrocarbons? Sir, aromatic hydrocarbons are those which contain one or more benzene rings. Very good, Rahul. Today we will learn about aromatic hydrocarbons. Come, let's start. Objectives. At the end of this lesson, you will be able to explain aromatic hydrocarbons, recognize and write structures of isomers of aromatic hydrocarbons, comprehend the structure of benzene, explain aromaticity, understand mechanism of electrophilic substitution reactions of benzene. Predict the directive influence of substituents in monosubstituted benzene ring. Learn about carcinogenicity and toxicity. Aromatic hydrocarbons. Aromatic compounds are a class of hydrocarbons that possess much greater stability than their conjugated unsaturated system suggests. The simplest example of this class of compounds, benzene, was isolated from illuminating gas by Michael Faraday in 1825. In the years to follow, this compound and homologues were isolated by the distillation of resin gums from balsam trees. Because many of the resin gums had fragrant aromas, these compounds were often called aromatic compounds or aromatic hydrocarbons and are also known as arenes. In 1845, August von Hofmann isolated benzene from coal tar. This isolation method remained the chief source of benzene until 1950s. Today, most benzene is produced from petroleum. Simple aromatic hydrocarbons come from two main sources, coal and petroleum. Coal is a complex mixture of a large number of compounds, most of which are long-chain compounds. If coal is heated to about 1000 degrees Celsius in the absence of air or oxygen, volatile components, the so-called tar oil, are stripped out. By fractional distillation, benzene, toluene, xylene, and naphthalene as well as many other aromatic compounds are obtained. Isomerism. In benzene, all 6 hydrogen atoms are equivalent, so it forms one and only one type of monosubstituted product. When 2 hydrogen atoms in benzene are replaced by 2 similar or different monovalent atoms or groups, then 3 different position isomers are possible. First one is 1, 2 or 1, 6, known as the ortho. Second one is 1, 3 or 1, 5 as meta. And the third one is 1, 4, known as para, disubstituted compounds. Nomenclature. Naming aromatic compounds isn't quite so straightforward as naming chain compounds. Often more than one name is acceptable, and it's not uncommon to find the old names still in use as well. The benzene ring. All aromatic compounds are based on benzene, C6H6, which has a ring of 6 carbon atoms and has this symbol. Each corner of the hexagon has a carbon atom with a hydrogen attached. A. The benzene ring is named as a phenyl group when it is a substituent. B. Multiple substituents on a benzene ring are numbered to give these substituents the lowest possible numbers. When only 2 substituents are attached to a benzene ring, they can be named by the common nomenclature using ortho, O-, 1 to 2 placement, meta, M-, 1 to 3 placement, or para, P-, 1 to 4 placement. Given compound is 1-ethyl, 2-methylbenzene, O-methylethylbenzene. Can you name the given compound? It is 1-ethenyl, 3-methylbenzene, M-methylethynylbenzene. Nomenclature of alkenes 2. C. Some common names involving benzene rings that you should know are toluene and orthoxylene. Biphenyl. Notice the numbering convention for this compound. D. Polycyclic aromatic hydrocarbons that you should know are naphthalene. A common nomenclature if only one substituent is on the naphthalene ring system involves the use of alpha and beta. E. The annulenes are large aromatic rings that have 4N plus 2p electrons in a cyclic conjugated system. That is, N is equal to any whole number including 0. The compound 1,3,5,7 cyclooctatetraene is not an annuline. It has 8 p electrons which would yield 1.5 for N. Structure of 10-annuline. Structure of benzene. A chemist, Kekulé, in 1865 suggested the following structure for benzene. According to Kekulé, 6 carbon atoms in benzene are on the 6 corners of a regular hexagon. Each C atom is attached with one H atom. There are 3 alternate double bonds between 2 C atoms to complete 4th vacancy of carbon. There was an objection to the above-mentioned structure of benzene that it must give 2 orthoisomers, di-substitution, but in actual practice only one orthoisomer is obtained. To answer this question, Kekulé extended his theory and argued that the position of double bond in benzene is not fixed, but the double bond system is revolving over the hexagonal ring. He proposed the given structures and said that all C-C positions have a partial double bond character. In the extension of his theory, Kekulé explained that C atoms in benzene were in a state of vibration, and due to this vibration, each pair of C atoms has a single bond half of the time and a double bond the other half of the time. Kekulé's structure failed to explain why benzene with 3 double bonds does not undergo addition reactions like alkenes or alkynes. Resonance 1. Modern instrumental studies confirm earlier experimental data that all the bonds in benzene are of equal length, approximately 1.40
picometer.
1
Picometer
equals 1 into 10 raised to the power minus 12 meter. This bond length falls exactly halfway between the length of a carbon-carbon single bond, 1.46
picometer,
and a carbon-carbon double bond, 1.34
picometer.
In addition, these studies confirm that all bond angles are equal, 120 degrees, and that the benzene molecule has a planar or flat structure. Modern descriptions of the benzene structure combine resonance theory with molecular orbital theory. Resonance theory postulates that when more than one structure can be drawn from the same molecule, none of the drawn structure is the correct structure. The true structure is a hybrid of all the drawn structures and is more stable than any of them. The greater the number of structures that can be drawn from a molecule, the more stable the hybrid structure will be. The difference between the calculated energy for a drawn structure and the actual energy of a hybrid structure is called the resonance energy. The greater the resonance energy of a compound, the more stable the compound. The 2 Kekulé structures that can be drawn from the benzene molecule are actually 2 resonance structures. The hybrid of these structures would be drawn as this, where the circle represents the movement of the electrons throughout the entire molecule. This delocalization of pi electrons found in pi molecular orbitals, is also found in conjugated diene systems. Like benzene, the conjugated diene systems show increased stability. Because of resonance, the benzene molecule is more stable than its 1,3,5 cyclohexatriene structure suggests. This extra stability, 36 kilocalories per mole is referred to as its resonance energy. Orbital picture of benzene. Because experimental data shows that the benzene molecule is planar, that all carbon atoms bond to 3 other atoms, and that all bond angles are 120 degrees, the benzene molecule must possess sp2 hybridization. With sp2 hybridization, each carbon atom has an unhybridized atomic p orbital associated with it. The overlap of the sp2 hybrid orbitals would create the sigma bonds that hold the ring together, while the side-to-side overlap of the atomic p orbitals can occur in both directions, leading to complete delocalization in the pi system. This complete delocalization adds great stability to the molecule. Molecular orbital theory predicts that overlapping 6 atomic p orbitals will lead to the generation of 6 pi molecular orbitals. 3 of these pi molecular orbitals will be bonding orbitals, while the other 3 will be anti-bonding orbitals, as shown in the figure. The 3 low-energy orbitals denoted pi1, pi2 and pi3 are bonding combinations, and the 3 high-energy orbitals denoted pi4, pi5 and pi6 are anti-bonding orbitals. 2 of the bonding orbitals, pi2 and pi3, have the same energy, as do the anti-bonding orbitals pi4 and pi5. Such orbitals are said to be degenerate. Because the electrons are all located in bonding orbitals, the molecule is very stable. Additional stability occurs because all the bonding orbitals are filled and all the pi electrons have paired spins. Molecules that possess all these characteristics are said to have a closed bond shell of delocalized pi electrons. Molecules such as benzene that possess a closed bond shell of delocalized pi electrons are extremely stable and show great resonance energies. Aromaticity. Aromaticity is a property of conjugated cycloalkenes in which the stabilization of the molecule is strong due to the ability of the electrons in the p orbitals to delocalize and act as a framework to create a planar molecule. The 3 general requirements for a compound to be aromatic are: 1. The compound must be cyclic. 2. Each element within the ring must have a p orbital that is perpendicular to the ring, hence the molecule is planar. 3. The compound must follow Huckel's rule. The ring has to contain 4n plus 2 p orbital electrons. Among the many distinctive features of benzene, its aromaticity is the major contributor to why it is so unreactive. The delocalization of the p orbital carbons on the sp2 hybridized carbons is what gives the aromatic qualities of benzene. Preparation of benzene. By the decarboxylation of sodium benzoate. This method is used in the laboratory to obtain benzene. Sodium benzoate is heated with soda lime, and when it gets decarboxylated, that is, removal of carbon dioxide, benzene is obtained. By heating phenol with zinc. When phenol vapors are passed over heated zinc dust, benzene is formed. By polymerization of ethine, acetylene. When ethine or acetylene is passed through a red-hot copper tube, it polymerizes to benzene. By the hydrolysis of sulfonic acid. Benzene sulfonic acid on hydrolysis with superheated steam gives benzene. Physical properties. Aromatic hydrocarbons are non-polar molecules. They are usually colorless liquids or solids. The naphthalene balls are used in toilets and for preservation of clothes because they have unique smell and the moth-repellent property. Aromatic hydrocarbons burn with sooty flame. They are immiscible with water but are readily miscible with organic solvents. Chemical properties 1. Although aromatic compounds have multiple double bonds, these compounds do not undergo addition reactions. Their lack of reactivity toward addition reactions is due to the great stability of the ring systems that result from complete pi electron delocalization, resonance. Aromatic compounds react by electrophilic aromatic substitution reactions, in which the aromaticity of the ring system is preserved. For example, benzene reacts with bromine to form bromobenzene. The bromination of benzene. All electrophilic aromatic substitution reactions share a common mechanism. This mechanism consists of a series of steps. An electrophile, an electron-seeking reagent, is generated. For the bromination of benzene reaction, the electrophile is the Br plus ion generated by the reaction of the bromine molecule with ferric bromide, a Lewis acid. The electrophile attacks the pi electron system of the benzene ring to form a non-aromatic carbocation. The positive charge on the carbocation that is formed is delocalized throughout the molecule. The aromaticity is restored by the loss of a proton from the atom to which the bromine atom, the electrophile, has bonded. Finally, the proton reacts with the FeBr4- to regenerate the FeBr3 catalyst and form the product HBr. You can summarize this particular electrophilic aromatic substitution mechanism like this. Chemical properties 2. In another example of an electrophilic aromatic substitution reaction, benzene reacts with a mixture of concentrated nitric and sulfuric acids to create nitrobenzene. The reaction of benzene with concentrated sulfuric acid at room temperature produces benzene sulfonic acid. When benzene is treated with an alkyl halide in the presence of anhydrous aluminium chloride, alkyl benene is formed. This reaction is known as Friedel-Crafts alkylation reaction. The reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acid, AlCl3, yields acyl benzene. This reaction is known as Friedel-Crafts acylation reaction. Directive influence of a functional group in monosubstituted benzene 1. A monosubstituted benzene, when treated with an electrophile, could undergo 3 electrophilic aromatic substitution reactions. Each reaction yields a disubstituted benzene as the organic product, which can be identified using the descriptors ortho, meta, and para. A is equal to any substituent. E plus is equal to electrophile. If the relative yield of the ortho product and that of the para product are higher than that of the meta product, the substituent on the benzene ring in the monosubstituted benzene is called an ortho-para directing group. If the opposite is observed, the substituent is called a meta-directing group. Look at this example. We can see that the methyl group is an ortho-para directing group. Directive influence of a functional group in monosubstituted benzene 2. If electrophilic aromatic substitution of a monosubstituted benzene is faster than that of benzene under identical conditions, the substituent of the monosubstituted benzene is called an activating group. Under identical conditions, reaction 2 is faster than reaction 1. Thus, the methyl group is an activating group. All activating groups are electron-donating groups. Common activating groups are if electrophilic aromatic substitution of a monosubstituted benzene is slower than that of benzene under identical conditions, the substituent in the monosubstituted benzene is called a deactivating group. Under identical conditions, reaction 2 is slower than reaction 1. Thus, the nitro group is a deactivating group. All deactivating groups are electron-withdrawing groups. Common deactivating groups are carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons which have 2 or more benzene rings fused together are toxic and possess carcinogenic or cancer-producing properties. Incomplete combustion of organic materials like tobacco, coal and petroleum leads to the formation of such polynuclear hydrocarbons. Cancer is caused when they enter the human body and undergo biochemical reactions and damage the DNA. Some of the carcinogenic hydrocarbons are Did you know? Benzene was first discovered by Michael Faraday in 1825, who called it bicarburate of hydrogen. In 1833, it was discovered again by Eilhard Mitselrich, who distilled it from gum benzoin. That's how it gets its name. Since it dissolves many organic and greasy substances, benzene found widespread use in removing paint and organic stains from metal surfaces. In 1849, Charles Mansfield perfected a method for extracting benzene from coal tar on industrial scales. Summary. Let us summarize what we have learned. Aromatic hydrocarbons, despite having unsaturation, undergo mainly electrophilic substitution reactions. These undergo addition reactions only under special conditions. Benzene and benzenoid compounds show aromatic character. Aromaticity, the property of being aromatic, is possessed by compounds having specific electronic structure characterized by Huckel's rule, 4n plus 2 pi electron rule. The nature of groups or substituents attached to benzene ring is responsible for activation or deactivation of the benzene ring towards further electrophilic substitution and also for orientation of the incoming group. Some of the polynuclear hydrocarbons having fused benzene ring system have carcinogenic property.